Bismillahirrahmanirrahim. Assalamualaikum and a very good morning to all. So I hope everyone is in good conditions in this MCO 2.0. So for today, MACE Tech Talk, I'll be sharing my work. So the title I would like to share today is Development of Nonlinear Extended Observer-Based Control for Quadrotor Under-actuated System. I am Dr. Elya Binti Mohd. So a little bit about myself first. So I'm a senior lecturer in Faculty of Engineering, University Pertahanan Nasional Malaysia. I'm married with 3 kids. I have 1 son and 2 daughters. About my academic background, I graduated, I had my first degree from UTP in 2003, and then I did my master's in UKM in 2009, and I had my PhD in University Putra Malaysia in 2018. So I have a little bit of working experience in the industry, where I work in the cogeneration plant in KLIA, which is a subsidiary, Petronas subsidiary. So it was in 2003 until 2009. So the title, why I'm sharing the title of my PhD thesis today, because this is what I'm going to share for the Tech Talk for today. So the title of my PhD thesis is Extended High Gain Observer-Based Output Feedback Control of Under-actuated Quadrotor. So during my PhD work, I get the chance to do attachment, student attachment. So in Michigan State Universities, under guidance of Professor Hassan Khalil. So if you know Professor Hassan Khalil, he's a book author for Nonlinear System, which is in 2003, and also a book author for Nonlinear Control, where he just recently published that books in 2015 during my visit. So the Tech Talk for today is mainly to share about my PhD works and how it's progressed, what the research that I'm currently working on today, until today. So the outline of my sharing today is, firstly, we're going to talk about the under-actuated system, what is under-actuated system, and then why Quadrotor UAV, and then why observer-based controls that is of interest for me. And then I'm going to share about the major steps on the development of observer-based control. And then, so we're going to go through each steps, where the first one is on the nonlinear control design framework. And then after that, we implement the implementing of observer-based control, where we implement the algorithm that we have already designed, and then we validate the algorithm that is being implemented. We validate in the flight testing, where I did the validations in 2 areas, which is indoor space, and then also at the wind tunnel, at the outdoor wind tunnel, to see the robustness of the algorithm. Okay, under-actuated system. So what is under-actuated system? Under-actuated system, in this class I will share that under-actuated system can be, you can look at it, it is available. It can be in the unmanned aerial vehicle and also in underwater vehicle, and it also can be in the ground robotics. Okay, so my focus is on the unmanned aerial vehicle here. So in unmanned aerial vehicle, where we call it UAV, there are two types of, in general, there are 2 types of flights, right? So the VTOL, which is vertical takeoff and landing, and also fixed wing. Okay, so in vertical takeoff and landing, we have, for example, helicopter, ducted fan, and quadrotor. Okay, so in my study, I focus mainly on quadrotor, vertical takeoff landing, because this is a good example of under-actuated system, and also that is of interest in the control communities nowadays, right? So the framework that I'm proposing in this Quadrotor is the control framework and validation is EHGO-OFB. Means that the extended high gain observer and with output feedback control, which is mainly to focus on the trajectory tracking of the Quadrotor during flight. Okay. So why Quadrotor UAV? Okay, so there are 3 reasons why I choose Quadrotor UAV. Okay, the first one is due to its under-actuation property. So under-actuated property is something that is strong interest in the control community. So opposite to under-actuated property is a fully actuated. So what is the difference between under-actuated and fully actuated? Fully actuated, it means that you have one control input to control one variable output. But for under-actuated, you have small number of control inputs to control a large number of variables, control output. So that is under-actuations, that is under-actuated, and the control is challenging. So apart from that, Quadrotor UAV, I choose it because the potential application of Quadrotor UAV is very wide. So for example, it is in the search and rescue mission, in remote sensing, in construction, in infrastructure inspection, in real-time monitoring traffic, road traffic. But it has strong potential to replace humans in all these missions, to be the first eyes for the humans before sending the humans to do any job there, right? So, but the challenges for Quadrotor UAV is that the challenges for Quadrotor UAV or any UAV is that it is small. Okay, so it has a very limited payload, and also it has energy limitation. Energy limitation, which is means that it can only fly at certain time. The flight time is limited. So this is the challenges that I'm interested in and address in my research. Apart from that, Quadrotor UAV nowadays we have off the shelf. It can be assembled. Okay, we have it through the commercially available devices. We can buy and then assembles and then set up whatever missions that we want. Okay, so there's so many things that is available off the shelves and it's low cost. So this is why I embark in the Quadrotor UAV study. Okay, so why observer-based control for Quadrotor? Okay, why? So observer-based control, it means that for Quadrotor UAV, it is, as you see here, it flies. Okay, it is very small. It is small, and it needs to add up monitoring sensors, whatever things to help to assist the human to check, to evaluate, to monitor some areas, for example, right? But the payload for the Quadrotor UAV is very limited. The more sensors you add to it, okay, the more battery it will consume, and hence you're going to have a smaller flight time, right? So to have a good control, we need all kinds of sensors. For example, to control the Quadrotor, in this mission, we may need position sensors, velocity sensors, so we can control the velocities, we can control the positions, and then also acceleration sensors. But in real practical application of Quadrotors, it is quite impossible to install all the velocity sensors, acceleration sensors, mainly to cater the control algorithm. So this is why observer-based control comes in. Observer-based control, it means that we utilize the existing sensors, for example, position sensors, and we estimate the position, the velocities, and also the acceleration, so that we are able to use the control algorithms to assist the Quadrotor's trajectory tracking during flight. So this is the examples of one examples of the Quadrotors is flying and at the open sea. So you can see that it will have very limited. It will consume a lot of energy to overcome the wind, right? So here is also so we need in the Quadrotor design, we need a small compact. We need try to find the embedded a control algorithm that gives a smaller control effort. Okay. So this is the showing the axis of the Quadrotor. Okay, the motion axis, which is the upward Z, and also the forward motion, which is X, and also the sideward motion, which is Y. So Quadrotor UAV, it is a 6 degree of freedom. Okay, so it is X, Z, X and Y, and then also roll pitch, and yaw. So the role here is to move the quadrotor, to tilt the quadrotor towards the front, and then the side word is pitch, roll, pitch, and yaw. Okay. Okay, so a little bit about the block diagram of quadrotor. So this block diagram is focusing only on the under-actuated part of quadrotor. So you can see here, this is the whole quadrotor. So the under-actuated part inside the quadrotor is actually in the forward motion and sideward motion. Where in this part, okay, we see here the control law, the actuators, and the actuators will produce 4 signals, which is the torque, the T here, which is to lift up, take off, and landing, and then the tau, roll, pitch, and yaw here is to control separately the angular, the tilting of the axis. For example, here is the tilting in the X, the tilting in the Y, and the tilting in the Z plane, right? So this is fully actuated. For this one is a fully actuated, but the under-actuated comes when, in order for you to move the quadrotor in the x-axis, in the forward or sideward, we need to tilt. We need to tell the quadrotor to tilt the angle, and then this angle, when it's tilted, then it can move to the position that we want. So it means that the challenge here, the under-actuated part here is in order to control the position, the movement position X and Y, the control torque has to tilt this angle, and then this one will move the another subsystem here, which is the X and Y motion subsystem. Okay, so this is the control law that we are looking at. Okay, so a little bit about the quadrotor nonlinear model. So it is a quadrotor is a 6 degree of freedom. So this is the model. We can find the model. There's lots of literatures that you can find the model. For example, I choose Bao Abdallah, and also there are others. For example, from the Italy, they have their models. Yeah, and then also Bao Abdallah is they have a very simple models that's been developed in 2004. Okay, so this is example of quadrotor nonlinear model. Okay, now we come to the main area here, which is the development of observer-based control for quadrotor under-actuated system. In the development of this observer-based control, we are looking at, I would like to share, there are 3 main parts towards this development of observer-based control. So the first one is on the control design of quadrotor, okay, which is using nonlinear approach, and the second is on the implementing the control design into existing quadrotor flight, and the third is on the validating the control algorithm, which is a flight testing in indoor space and outdoor. Okay, so let's go to the control design first. So in the control design of quadrotor using nonlinear approach, I would like to share the 3. I would like to classify into 3 major parts. The first one is we need to transform the quadrotor nonlinear model into under-actuated cascade normal form. So this is the under-actuated cascade normal form, where it has 2 subsystems. The first subsystem 1 and the second subsystem, which is cascaded. Okay, the cascaded where this the X4 here, the angular the X4 here is also will be also affecting this subsystem 1, if you see S1 and S2. And also the control algorithm, the control input is only at U here, which is at subsystem 2. Okay, so this is example, this is a general a normal cascade normal, which is under-actuated cascade normal form. So we look at this cascade normal form, and we look at the quadrotors, and we see that how map the variables that is related to each of these. So for here, the input is U, which is the input to this, the input is the top of the theta here. See, the one that what we want to tilt the quadrotor to move forward, and also the top at the roll, which is the one that we want to tilt the quadrotor to move sideward. That it will be the control input U here. And the output here, which is X1 and X3, is actually a vector of X and Y, which is the output quadrotor position, and also the output quadrotor angular position, which is theta and phi. So it is a complex system, Quadrotor is a multiple input, multiple output, because it has a vector. The x1 here is actually a vector of x and y. Okay. So then next is on the design Quadrotor stabilizing law in state feedback, then output feedback, and design the observer, which is in my case, in my work, I did the design using a standard high gain observer. So in the state feedback control, okay, so this is the control input. Now, in the state feedback control, there are so many non-linear control approach that we can use in the state feedback. For the state feedback design, there is a backstepping, sliding mode controls, and we can find it at the non-linear control books authored by Professor Khalil. He has all the techniques. But in order to state feedback control, state feedback design is to develop the control algorithm, which is the theorem of the control. In order to implement the control, okay, there are so many areas that we need to look at. Okay, for example, if we have the state feedback control, it means that all the variables x1, x2, x3, x4 is needed to in the control algorithm. But in the practical applications, for example, Quadrotor, we may have limited sensors. We may only have sensors for x1 and x3, but x2 and x4 we don't have, right? So this is where the output feedback control comes in. So in output feedback control, the sensors that we don't is not available, we are able to estimate it. So this is how we did the estimation, is through the observer algorithm, which is EHGO. In my case, I use EHGO, where this is the algorithm for the EHGO. So from these algorithms, we are able to estimate the x2 here in the output feedback control, and then also the x4. The saturation here shows is the limitation of the algorithm EHGO, where it has some peakings. So I will not share here, but if you like to know more, then you can, I have my contacts towards the end of my presentation. So the last part of in the control design framework is generally a performance recovery of EHGO output feedback versus state feedback. In this part, we are, if you are working on the development of the theorem, theory, for example, designing the control algorithm in state feedback, okay, you may need to do some proof of theorem. So for this one, we are comparing performance recovery. We are comparing how close our control algorithm of output feedback, how close is it to the state feedback. So if, for example, for state 1, this is one example of state response, where the position, it moves from 2 supposed to go to 0. So this is the state feedback algorithm. So assuming that in our Quadrotor we have we have all the sensors that is needed by the control algorithm. So this is the kind of output. This is the kind of response that we get, which is a small overshoot and a faster response. But when we use the output feedback, when we estimate certain sensors, so this is the kind of output response that we get. So as you can see here, that in EHGO output feedback, the main parameters that we need to tune is the epsilon here. So you can see that as the epsilon is reducing, so you will get a much closer response, closer to the state feedback response. So this is one steps that how we validate our output feedback control to the state feedback control. So next is on the implementation of control algorithm into existing Quadrotor flights. So prior to implementations, we need to understand on the Quadrotor actuators. So as you see here, the actuators, Quadrotor, it has 4 rotors, 1, 2, 3, 4. And this is the motion of the forward motion, which is in the x-axis, and this is how the rotors, the speed of the rotors in the sideward motion, which is y-axis. So this is the algorithm. Okay, usually in the Quadrotors, it has built-in how we want to move it forward and sideways. So we are actually only taking care. I'm only taking care on this one, the top to the top that is moving the forward, and then top that is moving the sideward. This is the Indoor Satellite and Space System Lab of Aerospace Department. This is available in UPM. So the overall, the existing Quadrotor setup consists of, we have an OptiTrack motion tracking system here, and it has at the ground control, it has PC and XB, which is wirelessly communicated to the Quadrotor. So, and then also the Quadrotor will be flying in the indoor space. So how it goes is that in my work, I use DJI 450 platform, which is the weight is 1.2 kg, and the flight controller is 3DR Fixhawk, and then the battery is LiPo battery, okay, which is able to hover for 15 minutes. So in this setup, the OptiTrack is measuring the position and attitude of the Quadrotor during flight. If you can see here, the OptiTrack up here, it is always continuously tracking the position and attitude, and then it gives the signal, which is Y1 here, which has all the positions and attitude of the Quadrotors. It gives the signal to the ground PC station, and so the ground PC station through ZigBee will transmit will compute the signals. Okay, so the output feedback control is at the ground PC station. So it will compute take the signals and compute the output feedback control, and the control signals will be sent wirelessly to the Quadrotor. So this is the how the block diagram of the EHGO that is in the discrete form. Okay, so the EHGO that is transformed into discrete form here, where if I Q1, Q2, Q3, and it has some gain here where we need, at the end, this is the K1, K2, K3, the gain that we need to tune to make sure that the EHGO able to estimate the derivation, to estimate the variables that we need. Okay, so there is another parameters which is K2 and K3 that we need to tune. So at the end is the observer-based control algorithm implemented into Quadrotor flight is like this, which has, if it has MU here, another constants here, where we and then also a saturation of all these control signals here. Okay, so this is the output, the variables from the sensors, and this is the estimated variables from the EHGO. And also it needs some saturation because the Quadrotor in the actual actuators, actual Quadrotor, the rotors has limitation, RPM limitations, for example 1500 to minus 1500. But when the challenge when we use observer-based control is that it may incur peaking during the first start of the estimation. So we need to saturate, we need to cut off that peaking, so that's why the saturation comes in. So this is the block diagram of actual flight setup. So you have the Quadrotor motion forward and sideward, which is, it gives the position X and Y, which is in the actual Quadrotor we have that sensors for position X and Y, and then the position X and Y will be measured by the OptiTrack, and then the OptiTrack will send the signal to the ground PC, and then this is the ground PC station where the computations of this yellow part here, EHGO, that is discretized, and also the control part here, and then the output will be, which is U, the control signal U here will be transmitted wirelessly to Fixhawk controller inside the Quadrotor, and also the Fixhawk will send the signal to control the actuators, which is the 4 rotors, and the actuators will control the forward and sideward motions according to the algorithm. Okay. So now we go to the last part is on the validations, flight testing. So in my work, I did the validations and indoor space and also outdoor, which is at the wind tunnel. So which is trajectory tracking. So the performance specifications that I'm looking at is the settling time, which is how fast the Quadrotor responds to the commanded trajectory during transients. The control effort is that the magnitude of control effort that by the controller to drive the Quadrotor to the commanded positions, and the position error is where how close the Quadrotor able to keep its position near to the commanded trajectory during steady state. It means that how close is it during hovering. But we don't want the Quadrotor to hovering at a large radius, because if, for example, if it's going to use it at the small compact areas, so if it's hovering at a very large areas, then it may knock the walls, and it will break the quadrotors, right? So, and also another last parameter is control effort steady state, which is the magnitude of control effort by the controller needs to keep the quadrotor hovering at the commanded position. So this is also another criteria that I'm looking at. When it's hovering at the steady state, when it hovering on air, okay, what is the control, how much control that is consumed? Because as we said that we are trying to find the control algorithm that can give a longer, that will gives what is say smaller control effort. Okay, so this is the experiments conducted. So I did 2 experiments, which is the first one is a point-to-point trajectory, and then the second one is a square point trajectory, where in the first one, point-to-point, so we have the quadrotor here, and then the fan, just a normal fan, it blows, and then the quadrotor is trying to move from position 0 to position 1. And the square point trajectory, so now it moves autonomously from one positions for motion 1, motion 2, motion 1, motion 2, motion 3, and motion 4. So it moves, motion from 0, it moves to motion 1, motion 2, motion 3, and motion 4. It moves autonomously. Okay, we only control it through the ground stations, and along the way it has a disturbance. The blue here is the winds disturbing the so this is the results that we obtained. So in this part, the result we obtained here is using the observer-based control EHEO. So as I mentioned, is we only use the normal fan in the indoor space. So if you can see here, the position error, the EHEO, the observer-based control that we added to the existing flight controller, hierarchical flight controller, is compared with the existing flight control. So you can see that the observer-based control, it gives a little bit slightly higher peaking at the initial stage, but at the end it goes, the shape is, it gives the quite close output response. So this is a position error X and position error Y, and then also this is the angular error for comparison between the observer-based control and then also the existing flight control. So this is the teams that working on the myself and also my students in the indoor space. Okay, then following to that, alhamdulillah, I get the chance to study the robustness of the observer-based control at the outdoor space, where in this part I did the study in the wind tunnel in UPM, where the OptiTrack, the cameras, the setups is being installed at the exhaust part of the OptiTrack wind tunnel here. And so we use the existing setup, it's just that it's transferred into the wind tunnel area here to study the robustness of the Quadrotor control observer-based algorithm to overcome a more challenging environment, wind environment. So this is the layout setup, okay, in the outdoor space. So as you can see here, this is one of the testing being performed. So this is back so that 9 study is we have a fixed flight procedure, fixed flight environments, and then also the Quadrotor's trajectory tracking is fixed, and then we did perform several studies comparing between the observer-based control and also using observer-based control using hierarchical EHEO, and also we compared with the existing flight controllers that is available inside here. So the result is very interesting. Yes, it addressed the energy limitations. I think I have it you may look at my publications. So this is the trajectory tracking. This is the three-dimensional flight obtained from the outdoor testings. Okay, this is the obtained from the OptiTracks. So if you can see here, this one, the Quadrotor is takeoff and then is hovering, and then there's another part is also takeoff and hovering, but the radius is very large here, and this one the radius is very small. So what makes the difference is the type of batteries that being used in this flight testing. And also, so that means that the batteries that being used is also plays an important roles, okay, to help the control algorithm, to help gives a much better to performance. Okay, so I think that's all. So these are my related publications that you that would like to share. So details about the studies on the first one here is on the implementation of VHO in real time, and then also how the and then also how the evaluation of the Quadrotor flights at the open space wind tunnel. So if you have any questions, I'm happy to help. I'm happy to share with you. So this is my email, elya@upnm.edu.my.